Hello. In this video, we're going to consider how we can represent a line with an equation. So we're going to consider 3 points to start. We have the point 2,5, which I'm going to put on the grid right here. We have the point 3,9, so that goes at this point on the grid. And 4,13, which isn't quite visible the way I have this grid, but it's going to be somewhere up here-ish. Now those 3 points seem to be on a straight line, and I think I could join them and continue that line down. But what I actually want to consider is, well, first off, are they? Remember that a straight line consists of all the points that have a constant slope. So that means I can pick any 2 of these points, and I should always get the same slope. So if I name them A, B, and C, I'll label that on the graph as well, A, B, and C. Then the slope of AB, well, it's delta y over delta x. So from A to B, 5 to 9 is an increase of 4 vertically. And 2 to 3 is an increase of 1 horizontally, so this is a slope of 4. If I consider the slope of BC, well, 9 to 13 is a vertical increase of 4, and 3 to 4 is a horizontal increase of 1. So again, we have a slope of 4. In fact, I can continue this line by counting out. So if I consider what would happen if I was counting between A and B, vertical change 1, 2, 3, 4, horizontal change 1, I can basically figure out other points on the line by reversing this idea. So what if I go 1 to the left and then down 4? That puts another point here at 1, 1. If I go again to the left and then down 1, 2, 3, 4, that puts a point right here at 0, negative 3. Over 1, down 4, 3, 4, right here at negative 1, negative 7, and so on. So that line can continue. So any of these points with any of these slopes. Now I've just been going 4 and 1, but I could go, for example, up 2 and over half, or up 8 and over 2, anything that has a ratio of 4 to 1. So this whole line is made up of an infinite number of points. So there's the points I've written here that are actually perfectly on the grid, but there's also all the points in between them. And between any 2 points, I can actually put another point in between them. And between those 2 points, I can put another point in between them. So there's an infinite number of points that we join them together to show that there's no end to the points that I can pick. But what all these points have in common is when I pick any 2 of them, I will always and forever have a slope of 4. Well, this is how I can write the equation of the line. Because let's say, for example, that we have some hypothetical point on this line, x, y. So these are the general coordinates of any point on the line. What I want an equation that relates the values of x and y, tells me what the rule is between these 2 points for this particular line. Now we could try and kind of figure out this rule through a little bit of guess and check by considering, well, let's say, for example, I had the number 2. How could I use 2 to calculate 5? That could also be used with 3 to calculate 9, and it could also be used with 4 to calculate 13. We usually consider x to be our input variable. So that's the thing we're starting with. And y is our output variable, the value that gets calculated as a result of this. But I'm actually going to use the idea of slope to write this equation rather than just sort of guess and check. So slope tells me that I need delta y over delta x equals 4. And that's for any 2 points on the line. So let's say that those 2 points are some generic x, y, and then point A, so 2, 5. For delta y is the difference between y and 5. So delta y I could write as y minus 5. And delta x I could write as x minus 2. The change in the x values. I could also write it as 5 minus y and 2 minus x. That's not going to change anything as long as I am consistent in the order. If I've always started with the point xy, I have to start with that point. If I've always started with the point 2, 5, I have to start with that point. And these would have to equal 4. So technically what I've got here is an equation that represents this line. I'm going to isolate y. And the reason I'm going to isolate y is because, as I said, y is our output. In other words, we want it to be able to be an equation where I can put in a value of x and easily calculate a responding value of y. So I'm going to start by multiplying both sides by x minus 2, which turns this into y minus 5 equals 4x minus 8. When I distribute 4 times x minus 2. And then I'll add the 5 to both sides to get y equals 4x minus 3. This is an equation that represents every point on this line. And we can test it with the 3 points we have. If I substitute in x equals 2, well, 4 times 2 is 8, minus 3 is 5. And that is the y value I'm expecting when x equals 2. If I substitute in for, let's say, point C, x equals 4, I should get y equals 13. Well, 4 times 4 is 16, minus 3 is 13. So this equation works for all the points on the line. And you may notice, in fact, that this 4 here matches the slope. And it will always, because I had 4 times x here. So that coefficient there is the slope. I do want to also make a connection here with what we learned about polynomials. With polynomials, we talked about degree. And the degree of this equation is 1, because the y and the x both have powers of 1. So the degree of this equation is the highest power of a variable, which is just 1. And we called degree 1 polynomials linear polynomials. That is because of this relationship that we see here. If I have something that on a graph looks like a line, then the equation that represents it will have a degree of 1. And so we call that a linear polynomial, or a linear degree. So this is a linear equation. Another thing that I actually kind of want to notice here is specifically where this graph crosses the y-axis. This is called the y-intercept. The y-intercept is the value of y when x equals 0. And when x equals 0, 4 times 0 is just 0, so minus 3. This value right here, the constant term, is going to be the y-intercept for lines. All right, so let's go on to some examples where I know some things about two lines, and I want to be able to find their equations. So let's start with the equation of a line, there's only one possible line that has these criteria, a slope of negative 2/3, and it goes through the point 6, 5. So I only know one point on the line, but I do know the slope. And I know that any other point on the line will have to have that slope with the point 6, 5. So I'm going to consider the point xy. And I'm going to do what I did above, which is to say, well, the change in y, so y minus 5, over the change in x, which would be x minus 6, equals negative 2/3. Now, just for sake of convenience, I'm going to put the negative with the 2. It could go with the 3. It doesn't really matter. It just has to go with one of them. Because now when I multiply both sides by x minus 6 and by 3, so it kind of looks like cross multiplication. All cross multiplication really is multiplying both sides of the equation by both denominators. What I end up with is 3y minus 15 when I distribute the 3, and negative 2x plus 12, which means that 3y equals negative 2x. So negative 12 plus 15 is going to give me 27. And I'm going to divide by 3 so that I can isolate the y. So I get y equals negative 2/3 x plus 9. So that is an equation that represents this line. Shouldn't be shocking here to see my slope show up as the coefficient of the linear term. And what I now know about this equation, I actually know a second point now about this line. I know that this line is going to go through the point 0, 9. That 9 has to be the y-intercept. So that would actually enable me to sketch it pretty accurately, because I know that it goes through 0, 9, and then it also goes through 6, 5. So that line is like this, roughly. All right, now I've been just writing this as, so y minus, and then I'm going to put like y1 to indicate that that's a specific y value that I know, over x minus x1 equals the slope. But the more common way that this is sort of expressed is to say, well, look, I know I'm going to want to multiply by this to isolate y anyway, so let's just do that right from the beginning. So the more common way that this is expressed is like this. This is called the point slope form of a line. It's where I have delta y essentially equals m times delta x. And that's essentially how we write the equation of a line. Now in this next case, I don't have the slope, but I do have 2 points. So I can go ahead and find the slope from the points. So between these 2 points, I know that the slope has to be delta y. So from -7 to 5 is an increase of 12 over delta x. From 0 to -3 is a decrease of 3. So my slope is -4. That means that if I use this whole point slope form thing, I've got y minus -7 equals the slope, which is -4, and then x minus 0. Or I could have used the other point. I could have done y minus 5 equals -4 times, so y minus 5 equals -4 times x minus -3. Either one of these will give me the same thing, so I get y plus 7 equals -4x, which means y equals -4x minus 7. Or in this second case, y minus 5 equals -4. Now this is x plus 3. So -4x minus 12, which if I add 5, y equals -4x minus 7. So it doesn't really matter which point I use. Either one of them is going to give me the exact same thing. And in fact, here I could have shortcutted straight to the end because I was given the y-intercept. If you notice that, great. You can just, I have the slope, that's -4. I have the y-intercept, which is -7. You can at that point just skip straight to writing the equation y equals -4x minus 7. If you don't notice it, then you'll still end up there. You just do a little more work. So considering again, just generically, what do we know about the final equation once y is isolated? The slope is m. So the coefficient of the linear term. And more to the point, or further information, the y-intercept, in other words, where the graph is going to cross the y-axis, is b, the constant term of this equation.